Okay, so your entry slip asked you a grand question. We know that electrons have wave-particle duality. But how can we prove that? Explain how we know there's wave-particle duality.
Because of the double slit experiment.
So what happened in the double slit experiment to prove that there is wave-particle duality for the electron?
When they weren't observed, they had an interference pattern.
So it had an interference pattern. So electron always has an interference pattern, so it's a wave. Not always.
There's an effector.
So when I observe it, what happened?
It acts as a particle.
Acts like a particle. So an electron can act like a wave or a particle?
Yeah. Something like that.
That makes no sense. How are you supposed to reason that out?
I don't know.
You know what?
It just happened.
It's a magical thing, and that's the perfect reason out. You can't.
You can't know everything.
No, it just happens. It chooses. Okay? So, what does that mean then? So, do I treat the electron like a negatively charged subatomic particle? Yes or no?
That's what it is, isn't it?
Yeah, it's a negatively charged subatomic particle. But do I treat the electron like it can be a wave?
Yeah.
Well, why?
Because it's also that.
It's also that. Listen, it's very confusing and difficult, but it's one of those things that it really opened the world of science. And this is like this right here is a lesson that I'm not ever going to quiz you on, but it's something nice to know. I like taking as much as I can in here, bring stuff real world, to make it apply to you. So if you heard of anything of quantum mechanics, quantum realm, all of that is because of this. This changed the whole world as we know it and completely flipped it upside down. Very confusing. Yeah. Because I have, typically on this day, I have 2 videos I like to show. My view board took forever to get going. So yesterday we talked about Heisenberg's uncertainty principle, and what does Heisenberg's uncertainty principle state?
You cannot find the location and velocity at the same time.
So the location and the velocity of an electron cannot be known at the same time. By finding one, we change the other. Got it?
Oh, I know a Heisenberg.
Not that one.
Are you trying to say something,
Tourists.
Mr. Hall?
Tourists that turn into scientists.
You want
Tourists
to eat all
taking
day?
photos that are
Because if
analyzed
you
by
keep this
AI,
conversation going, you're going to end up
so
with
researchers can help life underwater flourish.
That's what you'll be laughing when I stick you with 5 days a day.
The Heisenberg uncertainty principle is one of a handful of ideas from quantum physics to expand into general pop culture. It says that you can never simultaneously know the exact position and the exact speed of an object, and shows up as a metaphor in everything from literary criticism to sports commentary. Uncertainty is often explained as a result of measurement, that the act of measuring an object's position changes its speed, or vice versa. The real origin is much deeper and more amazing. The uncertainty principle exists because everything in the universe behaves like both a particle and a wave at the same time. In quantum mechanics, the exact position and exact speed of an object have no meaning. To understand this, we need to think about what it means to behave like a particle or a wave. Particles, by definition, exist in a single place at any instant in time. We can represent this by a graph showing the probability of finding the object at a particular place, which looks like a spike, 100% at one specific position, and 0 everywhere else. Waves, on the other hand, are disturbances spread out in space, like ripples covering the surface of a pond. We can clearly identify features of the wave pattern as a whole, most importantly, its wavelength. which is the distance between two neighboring peaks, or two neighboring valleys. But we can't assign it a single position. It has a good probability of being in lots of different places. Wavelength is essential for quantum physics, because an object's wavelength is related to its momentum, mass times velocity. A fast-moving object has lots of momentum, which corresponds to a very short wavelength. A heavy object has lots of momentum even if it's not moving very fast, which again means a very short wavelength. This is why we don't notice the wave nature of everyday objects. If you toss a baseball up in the air, its wavelength is a billionth of a trillionth of a trillionth of a meter, far too tiny to ever detect. Small things, like atoms or electrons, though, can have wavelengths big enough to measure in physics experiments. So if we have a pure wave, we can measure its wavelength and thus its momentum, but it has no position. We can know a particle's position very well, but it doesn't have a wavelength, so we don't know its momentum. To get a particle with both position and momentum, we need to mix the two pictures to make a graph that has waves, but only in a small area. How can we do this? By combining waves with different wavelengths, which means giving our quantum object some possibility of having different momenta. When we add two waves, we find that there are places where the peaks line up, making a bigger wave, and other places where the peaks of one fill in the valleys of the other.
Constructive and destructive interference.
The result has regions where we see waves separated by regions of nothing at all. If we add a third wave, the regions where the waves cancel out get bigger. A fourth, and they get bigger still, with the wavy regions becoming narrower. If we keep adding waves, we can make a wave packet with a clear wavelength in one small region. That's a quantum object, with both wave and particle nature. But to accomplish this, we had to lose certainty about both position and momentum. The position isn't restricted to a single point. There's a good probability of finding it within some range of the center of the wave packet. And we made the wave packet by adding lots of waves, which means there's some probability of finding it with a momentum corresponding to any one of those. Both position and momentum are now uncertain, and the uncertainties are connected. If you want to reduce the position uncertainty by making a smaller wave packet, you need to add more waves, which means a bigger momentum uncertainty. If you want to know the momentum better, you need a bigger wave packet, which means a bigger position uncertainty. That's the Heisenberg uncertainty principle, first stated by German physicist Werner Heisenberg back in 1927. This uncertainty isn't a matter of measuring well or badly, but an inevitable result of combining particle and wave nature. The uncertainty principle isn't just a practical limit on measurement. It's a limit on what properties an object can have, built into the fundamental structure of the universe itself.
Okay, so the reason I play this video, it explains it very, very well for you, is what's the Heisenberg uncertainty principle really meaning and talking about? The quantum world is different than what we call the macro world that we live in. I had a physics professor and we had a fun time with him because this is the equivalent of what he did with us, is we actually had to use the
Mr.
equation.
Hall?
Yes?
Who are the two that's wanting supper in your room?
I got Mason. My bad, I thought there's two. Hello?
There's not anybody?
Mason raised his hand, that's the only one.
Mason
Miller.
Miller. Is he staying after school for something?
That's gonna be a no.
Okay, because the past 2 days, everybody's signing up, and we've had to throw food away for 2 straight days because nobody's came and got it. And we only had 2 people that said they were staying after school today,
I got you.
but he's not.
No, you can cut him off.
Okay, thank you.
What's up?
That's after school, like you go in, you
Oh, I knew that.
play.
I knew that.
Yeah, I'm in.
I knew that.
Anyway. So, the, I totally took my train of thought. Oh yeah, so we actually had to use the equation, and here is the weirdest part of the world. We calculated, and there actually is a probability that I'm not just standing here in this room teaching chemistry to you today. I'm actually in Miss Steffi's room teaching environmental science. There is a mathematical probability to this. Here's the problem. The mass is what comes into effect. So when you look at momentum, momentum deals with mass. Because my mass is so great, the probability is super small. I'm talking it's like a billionth of a trillionth of a trillionth of a trillionth of a trillion percentile that I'm in there teaching environmental science. So does it exist? Yes. But am I in there teaching environmental science? No, the number is so close to zero, it's zero. Interesting, right? We actually calculated it. He gave us his mass. We had to actually calculate out his, we had to calculate out the probability of him in the next room teaching geology, which was interesting. So the difference comes in when you have things with super small masses of the subatomic scale. At the subatomic scale, that's where things changed. Which brought in the second scientist that we're going to talk about. This one might be a little familiar to you, and you may have heard of something of his, and we're going to discuss it. But this one, I always spell it. Schrodinger. So when you look at Erwin Schrodinger, he did something. Schrodinger went and he took and used wave-particle duality of electrons to treat our electrons like waves in atoms. He brought the wave-particle duality nature into real understanding. And he made something very useful from it. He came up with what is called Schrodinger's equation. And what Schrodinger's equation does is it gives us the first three quantum numbers. These three quantum numbers are the mathematical calculation of the area of the electron. So what these three quantum numbers give us, it gives us the orbital. This equation gives us the orbital. Where electrons are. Now, orbitals are confusing. You've heard this term. I've used this term. You've even asked me, what's an orbital? I've looked at you and told you the most simplistic breakdown definition of what an orbital is. It's the probability area of where And this opens our world completely up. So you remember the double slit experiment we talked about yesterday? And I talked to you about how the electrons, they thought the electrons were going through and interfering with each other, so they went one at a time. So then, sitting one at a time, they started to do some calculations. And they started to figure it out. And what happens is, everything opens up to a probability. So now everything has changed to where there's this probability that comes in. And that, of course you don't. Stupid Siri. Trying to understand chemistry. Ridiculous. Give a simple function. Hey Siri, give me a really good waffle recipe. This is what I found on the internet. Waffles are not crepes. Duh, Sherlock. Probability opened everything up for us. During the double slit experiment, they mathematically sat down. They went through and mathematically showed what was happening. And that's the funnest part in the world. Because they have the box, electrons, one at a time. There's an opening for them to go through. Remember, 2 slits. They got the interference pattern. See? Now, that's freaky and that's weird. But today we make it even more freaky and weird. Okay? Here's what is mathematically happening. We have the electron. The electron leaves from here and comes forward. From that one electron, it's in a state of what we call superposition. Here is what that electron does. Mathematically proven and shown. This electron comes through this slit. This electron comes through this slit. Same electron. That electron gets over here. That electron comes through the slit, back around, through this slit, back through, interferes with itself, and comes over here and hits. That same electron is hitting over here. That same electron is all the way over here, didn't even go into the pattern. That same electron is all the way over here, not even in the same room.
He's a wacky guy.
Same electron. As in all these different positions and doing all these different things. Mathematically is what it's doing. What brings us to the idea of the state of superposition. Superposition state. The Mr. Hall breakdown simplistic definition for you to get at the superposition state is this. The superposition state is the state of an electron in all possible areas and states all at the same time. it's literally the explanation. It's the mathematical thing. That electron is here. The 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 electron ain't even there. It just does whatever it wants. It's like a 13-month-old toddler. Whenever you look at her and you tell her, it's like, stop getting into dog food.
I think you're insane. I think you're going insane right now, Mr. Roll.
A little bit, man. This right here is nuts. How in the world do you tell me there's one thing, but that one thing is in multiple different things all at once? That's how it works. It's confusing, right? Let me break it down for you.
Wow.
Erwin Schrodinger is not famous because of his little equation. That's very complex, by the way. I'm not writing it all up here. Like, it's so complex whenever I was in P-Chem with Dr. Day. And Dr. Day was a very hard professor. Dr. Day literally looked at us and said, this is Schrodinger's wave equation that we're talking about. Mathematically, your skills aren't there yet for us to use this, so we're just be inspired. On to the next thing. Which at that moment, I'm like,
You mentioned the cat, Mr. Roll. Don't.
which brings me to what Schrodinger is famous for. What Schrodinger is famous for is Schrodinger's cat. What you have to get with Schrodinger's cat, before anybody comes at me, especially before I get canceled on YouTube, this is what we call a thought experiment.
What do you mean a thought experiment?
Means it's just something to think about. It has nothing to do. He didn't actually do this. Okay? It's a thought experiment. Here's how Schrodinger's cat goes. And here's how he explains the state of superposition. So his idea with this is to take a very complex concept that's happening here and get it to a point to where people would understand what was actually happening. So he created the Schrodinger's cat thought experiment, which is this. You have a box. We have a box. We have a cat. We put the cat inside the box. Once we put the cat inside the box, people have went different from here. They're like, you got a poison, you got a bomb, whatever. They put a poison or a bomb, something in there that's going to kill the cat. Thought experiment! He didn't do it. It's a thought experiment. So what he did is you set the bomb in there. It has a 50% chance of going off, a 50% chance of not going off within the next hour. You close the lid. Now, it's a soundproof box. You cannot hear if the bomb goes off or not. You tell me. It's an hour later. Is the cat alive or dead?
You don't know.
50-50.
I do know.
Well, you
But
know.
then tell me.
I do. But what do you think? Is the cat alive or dead?
Alive.
You think alive? Okay.
Nah, he dead.
You think dead?
Gotta be.
It's not that simple. The cat is in what we call a superposition state. You all get partial credit. The cat is alive. But the cat is dead.
So true.
The cat is alive dead, and the cat is dead alive. And the cat's not even in the box. Anybody that owns a cat knows what I'm talking about. Put those little felines inside of a box, and you'll be like, I promise you I put it in here, Mom. Doesn't matter. The cat is in all states all at once. Until I do what?
Open the box.
When I open the box, what happens?
You see it. Or
I can
you don't
see
it.
whether the cat is alive or dead, right?
Yeah.
I observed it, correct?
Mhm.
What happened in the double slit experiment whenever I put a device here that was going to observe the electron? It acted like a particle. It went back. Why? I collapsed the superposition state. If you do not get off that phone, I'm going to take both of them, lock it up in the office in the safe, and you ain't going to get it back to the end of the day. It doesn't matter. You collapse the superposition state. We collapse the superposition state, and that's it. We now definitely know where the cat is at, whether it's alive or whether it's dead. There's no debating.
Mr. Alt,
We can see it. It's the same thing with the electron. Leave the electron alone, it's in the superposition state. I put a device that's going to observe it, I instantly know. Oh, it went through the left slit, it went through the right slit, it went through the left slit, it went through the
Teachers,
right
pardon
slit.
interruption, but I need to see the following juniors in the auditorium. I need to see Caitlin Klein, Isabel Mullins, Joshua Reed, Kyla Sizemore, Molly Workman, Cynthia Atkins, Jeremy Daniels, Diego Mendoza, Logan Morgan, Kyler Short, Ethan Walls, Madison Ayers, Emily Reed, Brandy Wells, Braceland Hunt,
Tourists.
Caitlin Good,
Tourists that turn.
Michael Sellards, Ben Blankenship, Jerry Brown, Hallie Klein, Christina Frill, Jaden Hatfield, Marcus Lee, Zach Morgan, and Dakota Sampson.
Mr. Alt, I have but one thing to say to this experiment.
Make it fast.
You're wrong, because cats have 9 lives, so it's alive, but it's got 8 lives left. No matter what.
But the cat was also on its last life. And it was on its 5th
You
life.
got me there.
It was on its 8th life. Don't you get the idea? Superposition state, this thing just keeps going.
Austrian physicist Erwin Schrodinger is one of the founders of quantum mechanics, but he's most famous for some.
Oh, by the way, funny thing is, this concept is so confusing. If you walk out here confused and a little lost, don't feel bad. You know what Schrodinger did after this? He became a botanist.
Oh, wow.
He went from explaining this to studying plants,
Something he never actually did.
which is why they got the
A
little
thought
plant.
experiment involving a cat. He imagined taking a cat and placing it in a sealed box with a device that had a 50% chance of killing the cat in the next hour. At the end of that hour, he asked, "What is the state of the cat?" Common sense suggests that the cat is either alive or dead, but Schrodinger pointed out that according to quantum physics, at the instant before the box is opened, the cat is equal parts alive and dead at the same time. It's only when the box is opened that we see a single definite state. Until then, the cat is a blur of probability, half one thing and half the other. This seems absurd, which was Schrodinger's point. He found quantum physics so philosophically disturbing that he abandoned the theory he had helped make and turned to writing about biology. As absurd as it may seem, though, Schrodinger's cat is very real. In fact, it's essential. If it weren't possible for quantum objects to be in 2 states at once, the computer you're using to watch this couldn't exist. The quantum phenomenon of superposition is a consequence of the dual particle and wave nature of everything. In order for an object to have a wavelength, it must extend over some region of space, which means it occupies many positions at the same time. The wavelength of an object limited to a small region of space can't be perfectly defined, though, so it exists in many different wavelengths at the same time. We don't see these wave properties for everyday objects because the wavelength decreases as the momentum increases, and a cat is relatively big and heavy. If we took a single atom and blew it up to the size of the solar system, the wavelength of a cat running from a physicist would be as small as an atom within that solar system. That's far too small to detect, so we'll never see wave behavior from a cat. A tiny particle like an electron, though, can show dramatic evidence of its dual nature. If we shoot electrons, one at a time, at a set of two narrow slits cut in a barrier, each electron on the far side is detected at a single place at a specific instant, like a particle. But if you repeat this experiment many times, keeping track of all the individual detections, you'll see them trace out a pattern that's characteristic of wave behavior, a set of stripes, regions with many electrons separated by regions where there are none at all. Block one of the slits and the stripes go away. This shows that the pattern is a result of each electron going through both slits at the same time. A single electron isn't choosing to go left or right, but left and right simultaneously. This superposition of states also leads to modern technology. An electron near the nucleus of an atom exists in a spread-out wave-like orbit. Bring two atoms close together, and the electrons don't need to choose just one atom, but are shared between them. This is how some chemical bonds form. An electron in a molecule isn't on just atom A or atom B, but A plus B. As you add more atoms, the electrons spread out more, shared between vast numbers of atoms at the same time. The electrons in a solid aren't bound to a particular atom, but shared among all of them, extending over a large range of space. This gigantic superposition of states determines the ways electrons move through the material, whether it's a conductor, or an insulator, or a semiconductor. Understanding how electrons are shared among atoms allows us to precisely control the properties of semiconductor materials like silicon. Combining different semiconductors in the right way allows us to make transistors on a tiny scale, millions on a single computer chip. Those chips and their spread out electrons power the computer you're using to watch this video. An old joke says that the internet exists to allow the sharing of cat videos. At a very deep level, though, the internet owes its existence to an Austrian physicist and his imaginary cat.
Here's the fun part. It gets even weirder. Not gonna go into too much depth with it. We'll hit it on Monday. But there's something called, and stop me if you've heard this one before, quantum entanglement. Yeah, okay.
I've heard of it, but I don't know what it is.
So quantum entanglement is two things connected together, and they're literally connected together. And we talk about this, on the quantum realm. So I talked to you guys a little bit of foreshadowing here about the up arrow and the down arrow of the electrons. The reason that exists is because of the spin of an electron, which is known, we represent with the spin quantum number. What happens is, how many electrons can go in one orbital? There's two. So hit one, hit two. Okay? They spin in opposite directions. We can take those two electrons, split them apart, and it's the weirdest thing in the world. And they did this in California in two different universities. They split the electron apart. And they took the one electron at one lab and made it spin the other way. And they never did nothing to the other one. But as soon as they flipped the spin of the one, guess what happened to the other? It flipped its spin. We could take these two things across the universe, and they're still entangled together. You flip one, it flips the other. I know, freaky weird, right? But that's where we're going. Monday, we're going to hit quantum entanglement, and then we're going to start in on the 4 quantum numbers. Understand something, okay? Because you know how the electron configurations was a puzzle, and then you found the pattern, and now you got it? The Quantum numbers are the same thing, but you have to understand the conceptual part that brought us to doing the quantum numbers. A lot of concepts here. A lot of difficult concepts. You have to understand the 4 quantum numbers also. So don't just get caught up or hung up on that. Hang on to them.